relationship between temperature and pressure. So as shown in this picture, there's a flask filled with air, and around it is ice water. And as we heated the ice water, we used the temperature probe to measure temperature and the pressure probe to measure pressure. During that lab, we predicted that as temperature went up, pressure would go up. And here is the data here that was collected. If you would like to pause the video and copy down the data so that you can graph it, go ahead and do that now. The next thing we're going to do is graph this data on the next page. So here is graph paper. There are quite a lot of lines here, and yes, I wanted you to use the entire paper so that we could see the spread, because it does go all the way to 100 for the pressure. So to pick our scale for temperature on the x-axis, and we measure this in degrees Celsius, I think there was like 27 lines on the bottom, and some people's went all the way up to 50. So I think that you could probably count by twos along the bottom. Some people counted by threes. Okay. And then along the top, I think there was 38 lines, and the highest number I have from my data was 109. So to figure out what scale to use on the underside, you can simply just take your highest number and divide by the number of lines there are. So this got around 2.9, which you could round up to 3. So I would say that counting by threes, some people counted by fives as you go along the top. Okay, so what you should have seen though is that 90 wouldn't have been up until pretty far on the graph, and our first data points were up at like 101. Some people actually did get in the 90s, so I'm going to start here: 90, 93, 96, 99, 102, 105, 108. Okay. So as we're plotting our points then, let's say this started at 14.5 and then up to 101. So that'd be about here. Then I got 20. Okay, so once we have our points, the next step is to draw the best fit line. And a best fit line is not a connect the dots. The best fit line is the average of all the points. So I'm going to take my ruler and kind of try to make an average here. You can also utilize graphing software to correctly or more accurately figure out the slope and equation of the line. So my line's somewhat like this. Notice that I'm accounting for some outliers. Most of them were right around here, and then these were kind of the beginning points and the end point. And then I've also drawn it all the way over so that I can find my y-intercept, which was over here. Okay. So the next questions then ask about our line. So I need to calculate slope and talk about what's happening. So the next question was, based on the results of the graph, if temperature does something, then pressure does something. You could have used the words up or down, either way. But this is if temperature increases, then pressure increases. Or you could have said decreases and decreases, either way. Okay. Next we have Amonton's law then. Is this inverse or direct? Well, if one goes up and the other goes up, that means that they're doing the same thing. So this is called direct. The word inverse means opposite. So this is a direct relationship. Next, it wants us to use 2 points to determine our slope. So you're also covering this in math. So the slope, remember, is equal to rise over run. And the rise would be how much does it go up? Okay, how much is it going up versus how much is it going over? That's your run, okay? So in order to calculate up divided by over, we need a couple of points on our graph. So I'm going to pick this one because it's like right on the line. So this is 16, 102, and I'm going to pick, I guess this one. And this one is at, let me follow it down, 39, 111. Okay, so those are the 2 points I'm going to use. I'm going to copy them over here. I've got 16, 102, and 39, 111. Okay. So now using those 2 points, my first point was my lower point here, or my first point. This one here was then is the coordinates x1 and y1. And then my second set of data have the coordinates x2 and y2. And so when I'm calculating my rise over run, I'm looking for the change, right? So this is calculating the change from here to here and the change from here to here. So I need to subtract them. So this is the equation for rise over run is y2 minus y1 over x2 minus x1. And now I utilize the numbers I had here to substitute in. So my y2, my higher one was 111. Minus the lower y coordinate was 102, so that was the y part. And going across for the x's changed from 39 to 16. Okay.
What did you count by on the y-axis?
3s, but I could have done 5s. Yeah. Over here, then I've got 111 minus 102, so that's going to be 9 on top divided by 39 minus 16 on the bottom. I've got 23. And then don't forget that there was units on these. So on the rise was my pressure, and we measured those in kilopascals. And on the run, which was the x-axis, we measured that in degrees Celsius. Right, that was the temperature. Okay, a lot of people in their calculator saw this and put 23 over 9, but that's not what this is. This is a 9 over 23, so it's going to become a decimal. So I got a round 0.4, so I got 0.39 kilopascal change for every degree change in Celsius. Right? That's what that means. Which is why I knew that every 3 changes of these would about change one of these. Okay? The next question says, write the y-intercept from your equation for your graph. So just like we did in the last unit and then also in math, the y-intercept form is y equals mx plus b, right? So what do those letters mean? Y is your y-axis, m is the slope that we just calculated, x is your axis, and b is the y-intercept. So on our y-axis was pressure. So instead of y, I would say pressure is equal to a slope of 0.39 kilopascals for every degree Celsius times our x-axis. Our x-axis was temperature, okay, times temperature, plus b, which is your y-intercept, which we haven't found yet. We got to go find it. So that's why I made my graph go all the way across the line here. So where this intersects my y-axis, this is 90, oh, I skipped here to 96, let's say. 96 degrees Celsius, okay? Okay, this equation and lab that we did is pretty powerful in that we can now use this to solve for any pressure or temperature just by plugging it into the equation. So number 5 wants us to plug in what happens if y is 0 and y on our graph was pressure. So what happens if I remove all the pressure from the container? What would my temperature be? So let's plug in, we're going to plug a 0 in for pressure. So if 0 equals 0.39 kilopascals per degree Celsius times, I'm just going to write T for temperature, plus 96 degrees Celsius. Okay, so I have my algebraic expression. I need to solve for temperature. Okay, using PEMDAS. When you're moving things around for PEMDAS, when you're going to the opposite side, you actually do it backwards. So I would actually start with my adding and subtracting here. I've got to get this 96 out of here. I can't do this multiplication first. I have to move this. So I'm first going to subtract 96 from both sides. Okay. So adding, subtracting, right, that cancels on this side then. So I have negative 96 degrees Celsius equals, this hasn't changed, to 0.39 kilopascals per degree Celsius times temperature. Okay. Now I'm multiplying by my variable. So if I'm multiplying to get the 0.39 out of here, I do the opposite. So I'm going to divide both sides by 0.39 kilopascals per degree Celsius. Okay, so I do the same thing on both sides. I also use my units because I can see then that everything should cancel except what I'm looking for. Okay. So I've got negative 96 in my calculator then, right? I subtracted that first. So negative 96 divided by the 0.39, oops. I got negative 246 degrees Celsius. Okay. So, okay, well that was cool. Like, why did we do that? Number 6 says, explain the meaning of X. What did we just figure out? So we just figured out using our equation that if the pressure was 0, the temperature would be, and everyone should have had different data. Like this was using the slope that I made from Connor's graph, but other groups could have different numbers and therefore would have a different slope. But this one then, the temperature would be negative 246 degrees Celsius. So what I mean by you could have gotten something different, so in 11th period yesterday, every group did theirs separately, and we got this range of numbers here. So this was all the slopes that 11th period got yesterday, or on Tuesday. So you can see that it just depended on your measuring and how accurate you were, and then how good your best fit line was. There's an accepted value for this, okay? We watched the video about how this guy predicted absolute 0. Well, this is how he did it. So this is the prediction of absolute 0. However, if we did this over and over again and we were very, very precise, we should have gotten negative 273. Okay, so the accepted value is negative 273, but we got negative 246. So this is why you do things more than once in science. The thing that this also means is that if I was to continue to draw this line for this graph, what we really solved for was the fact that like this graph line could like keep going and going and going, and it would go down. And so the negative 246 would be like where it would cross the x-axis on the graph paper if we kept drawing that line all the way down, okay? And so that's how they predicted absolute 0 before we even knew that molecules existed, because they didn't have a microscope or an electron microscope. Okay, that was the lab for Amonton's law. The next section is utilizing the relationship we just found to do calculations and predictions. So with a highlighter here, we now know then that as temperature goes up, pressure goes up. That's Amonton's law. Here's the relationship here. That means they're proportional or direct. And we can then have these equations just like we did in Boyle's law, except this time pressure and temperature are proportional. In Boyle's law, they were inverse. So this time, if one goes up, the other goes down. Or, sorry, if one goes up, the other goes up. In Boyle's law, it was the opposite. So let's now utilize this equation that we have, and I'm going to do the example and the solution, and then we'll do 4 practice problems together as well. So the question says, a gas has a temperature of 100 Kelvin at a pressure of 700 millimeters of mercury. So it has this. So I can tell then that this is my initial, because it has this. So this is my initial temperature and my initial pressure. And it says what temperature is required to increase the pressure to 800. So this is what I'm changing it to. So what temperature? That would be my temperature 2, or my new temperature, and pressure 2 would be my new pressure. Okay? So once you've read the question, identified which thing is first and which things are second, you can then use either equation, it doesn't matter to me which one you use, to figure out what the new temperature or pressure is. So I'm going to write my equation, pressure 1, temperature 2 equals pressure 2 times temperature 1. So notice that the 1's and 2's are opposite in this case. And so now I need to carefully plug them in. My pressure 1 was initially 700 millimeters of mercury, and I'm changing that into my new temperature, which I don't know. The new pressure I need is 800 millimeters of mercury, and my initial temperature was 100 Kelvin. So now, using algebra, I'm just solving for my variables, so I know 3 out of the 4 variables. Since I'm multiplying it by 700 on this side, I need to move it to the other side by dividing both sides by 700. Okay, so that cancels it out from this side. I now have temperature 2 equals 800 times 100 over 700. You can see if you're doing this right because you can predict whether or not this answer is going to make sense. So my initial temperature was 100, and this ratio of 800 over 700 is going to make this get bigger because 8 out of 7, that's bigger than 1. And so if my pressure goes up, my temperature should go up, and this will go up. So I can tell that I'm doing it correctly. If it had gone down, then you would know that you were doing it wrong. So 800 times 100 in my calculator divided by 700. And then there was only 3 numbers that we started with, so we'll keep 3 numbers. So 114 Kelvin. Okay. Okay, a couple of things to note is that this has to be in Kelvin. Okay, if the problem doesn't give it to you in Kelvin, you're going to have to change it. So let's take a look over here on the next page. There are 4 practice questions. And we'll start with the first one. It says, what new pressure, so I'm looking for a new pressure, that's pressure 2, will a gas that's at 740 millimeters of pressure, so that must be my original pressure because it's at that pressure. What new pressure will this gas have if it drops from this to this? So I know that this is my temperature 1 and this is my temperature 2. And there's no number here, but we learned earlier in this unit that standard temperature is a number. It's also in one of the homework activities. So section 5.4 or 4.4 on standard temperature is 0 degrees Celsius. Okay, but there's a big but here. You have to be in Kelvin. Okay, so remember that to get to Kelvin, you're going to take degrees Celsius and add 273, which is what we just determined. Okay, so before I even plug these in, you should convert these. So 273 plus 50 gives me 323 for my temperature 1, and 0 plus 273 is 273. Okay, so you have to make sure that your temperatures are always in Kelvin when you do the math. Okay, so now I start with my equation. I have P1 T2 equals P2 times T1. We're going to plug in what we know. So we identified up here that pressure 1 was 740 millimeters of mercury. Temperature 2 is 273 Kelvin. That's my new temperature. I don't know pressure 2, that's what I'm trying to find. And temperature 1 is 323 Kelvin. So to solve this, I would need to move this over so that pressure is all by itself, right? I've got 3 out of the 4 variables. Pressure 2 is what I'm trying to find. So if I'm multiplying, I'm going to divide both sides by 323 Kelvin. Okay. And again, I can tell whether I'm doing it correctly because my proportion should make sense. Up here in the statement, my temperature goes from 300 to 200. So if temperature goes down, my pressure, which was 740, should also go down. And the ratio of 200 over 300, that's less than 1, so that will make this go down. So I am doing it correctly. So I have 740 times 273 divided by 323. So that's 625 millimeters of mercury. Okay. This would be a good time to pause the video and see if you can do the next one on your own, and then unpause the video when you are ready to solve it. Okay, the question says, what new pressure is needed to change a gas that's at 740 millimeters of pressure and 21 degrees Celsius to 100 degrees Celsius? So I'm looking for a new pressure, that's my P2, and it's at this initial pressure of 740. It's going from 21 to 100, so it's going up. So this is T1 and this is T2. We do need to change these into Kelvin, so 273 plus 21 gives me 294 for this one, and then 100 plus 273 is 373. Okay. Now I can substitute that into my equation. So I have P1 T2 equals P2 times T1. Pressure 1 was 740 millimeters of mercury times temperature 2 is my new temperature of 373 Kelvin. I'm looking for my new pressure, I don't know that one, and the temperature originally was 294 Kelvin. Okay. So now I can solve for the variable I'm looking for, which is P2. So I would divide both sides by 294 Kelvin. Okay, so that cancels. I can see if I'm doing this correctly. Temperature is going up, so pressure should go up. So 300 over 200, that is greater than 1, so that will make this number go up. So in my calculator, I have 740 times 373 divided by 294 is 9. I'm going to round that to 939 millimeters of mercury because I was looking for pressure. Okay? Again, go ahead and pause the video and attempt number 3 on your own, and then when you're ready, unpause it and see if you did it correctly. Okay, we got what temperature is needed, so that's what I'm looking for. That's a new temperature. To change a gas that's at standard temperature and standard pressure to 800. So it's already at standard temperature of 0 degrees Celsius and a pressure of 760. So if you had forgotten what standard temperature and pressure were, that's back in section 4.4. So standard temperature is 0 degrees Celsius, but I need that in Kelvin, so that's really 273 Kelvin. And standard pressure is 760 millimeters of mercury, and I'm changing it to a new pressure of 800. Okay, so nothing has really changed except which variable we're solving for. So I still have the equation pressure 1, temperature 2 equals pressure 2 times temperature 1. I'm plugging in what I know. My initial pressure is 760. My temperature 2 is what I'm looking for. My new pressure is 800. And my initial temperature was 273 Kelvin. So now that you have everything substituted in, it's the same thing. We all have 3 out of the 4 variables. This time I'm looking for temperature 2. Since I'm multiplying by 760, I need to divide both sides by 760. So this cancels. And so I now have 800 times 273 over 760. I can tell if I'm doing this correctly because pressure is going from 760 to 800. So pressure is going up. So I would need my temperature to also go up. And 800 over 760 is a fraction greater than 1. So yes, that will go up. So I have 800 times 273 divided by 760 gives me 287. And this millimeters cancel, I'm left with Kelvin, which makes sense because I needed the temperature. Okay, the hope is now that you can do number 4 correctly on your own. So pause the video, see if you can do it yourself, and then see if you did do it correctly. Okay, so number 4 says what temperature is needed, so that's my new temperature, to change a gas that's at 60 degrees, so that's my original temperature, and at 1,000 millimeters of pressure, to a new pressure of 800. Okay. Don't forget temperature has to be in Kelvin, so I'm going to take 60 plus 273 to get 333 here. Okay. So now, same thing, I start with the equation P1 T2 equals P2 T1. My initial pressure, it says, was 1,000 millimeters of mercury, and temperature 2 is what I'm trying to find. My new pressure is 800 millimeters of mercury, and my original temperature was 333 Kelvin. Okay. To solve for T2, I'm multiplying by 1,000, so I would divide both sides by 1,000. Okay. So that cancels. I now have 800 over 1,000. That's less than 1. So that's going to make this number go down, which is what I would need because the pressure goes down, temperature should go down. So 333 times 800 divided by 1,000 gives me 266 Kelvin. Okay. Okay, thanks for watching this video and making sure you can do this. I do have tutoring. You can email me to set up or come after school 3 to 3:30.